Video Lab Report Number 2 by Group 3A. Introduction/main ideas. Our research question was, how would changing the voltage in a circuit containing a motor affect the motor speed? The goal was to determine the effect of current on a motor by comparing the number of revolutions per minute for circuits with 1, 2, 3, and 4 batteries. Learning this effect will help us understand how the current and magnetic fields of a motor interact. Our main findings were that there were no correlation between increasing the amount of batteries in the circuit and the revolutions per minute of the motor.
The models for this lab were magnetic field, the right-hand rule, energy charts, circuit diagrams, and system schema. Magnetic fields are created by the flow of current. Wires carry current, which creates a magnetic field. We use this theorem to create a magnetic field with our motor. Using the right-hand rule, we determine the direction of force, magnetic field, and velocity. Using energy charts, we were able to see that potential energy was high at the beginning of the revolution, and in the middle, potential energy and kinetic energy are equal, and at the end, kinetic energy is high.
Magnetic fields, dipoles, and current loops. A bar magnet has two poles, north and south, and is a magnetic dipole. So basically there are two opposing charges separated by a distance, and they point from the north to south pole. Static charges generate these electric fields, and moving charges generate magnetic fields. Magnetic field lines from a current loop. These magnetic fields are created by moving charges, electrons spinning, and a current flowing. Magnetic fields and wire. Moving charges create these magnetic fields and are also affected by them. A wire with a current going through it has moving charges. So a current carrying wire both creates a magnetic field and is affected by it.
In this slide, we could see the system schema that shows the path of the electrons. On the right, we also see the circuit diagram, which shows the different trials that we carried out in this experiment. After each trial, we added another battery, starting with 1 and going all the way to 4.
Experimental design. In this experiment, we used batteries, a loop of wire, alligator clips, a stand for the wire loop, magnets, and a recording device. The loop was placed in the stand above the magnets. Alligator clips were then used to connect the batteries to the stand. The trials were different by their number of batteries. Each trial was recorded for 10 seconds and the number of revolutions were counted. Multiplying this number by 6 showed us the revolutions per minute for each trial. The realm of the model targeted was the ability to manipulate the current through a circuit containing a motor in order to determine the current's effect on a motor's speed, and our understanding of the interaction between electrical and magnetic fields. Possible flaws were that we used a human to count the number of revolutions, that the loop was not perfectly symmetrical, and that camera quality was low.
In terms of results and calculations, the only data available was really the number of 1.5 volt batteries included in the circuit versus the revolutions per minute of the copper wire loop. The way that revolutions per minute was counted was by counting the number of revolutions that we observed in 10 seconds of video footage, and then we used that number and multiplied it by the amount of seconds per minute to get number of revolutions per minute. These data points were then plotted, and a line of best fit as well as an R-squared value were found for the points in total. The line of best fit that was found in this experiment showed a negative trend line, which is counterintuitive to what we would have expected. Despite these findings, we see that the R-squared value is relatively low at 0.6, so that shows that there is a decent amount of variability in the results that we acquired throughout our experiment. This variability, again, could be attributed to some of the possible flaws that we explained in our experimental design.
Scientific reasoning. Since the underside of our wire is stripped, charges are able to move through it. We have learned that magnetic fields are able to exert forces on these moving charges, hence the magnets underneath the loop. These forces are able to push the stripped side of the loop perpendicular to the magnetic field. The coated side of the loop does not feel this same force, so the push is able to turn the loop over every time the stripped side is exposed to the forces of the magnetic field. Theoretically, as we increase the number of moving charges through the loop, we should be able to speed up the motor. By looking at the equation that follows, we can see that increasing current, I, should increase the magnetic force. This increased force would push the loop harder, leading to more revolutions per minute.